Hi everyone and welcome to this video on lenses. It's Mr. H here. Lenses are something that are all around us, and in fact some of you might even be wearing lenses as you watch this in the form of glasses. Lenses are transparent objects that cause light to refract. Now transparent just means that you can see through the actual glass, and then the refraction of light, as we know from previously, is the bending of light as it enters a new material. So that's what's happening in a lens. There's two types of lenses. There's converging lenses. They're thicker in the middle, so there you see it's thicker there, and towards the edge it's not as thick. These bring light rays together. Now these lenses are sometimes referred to as convex lenses, and it's for the same reason as mirrors, because if light was coming into a mirror that was curved this way, it would be a convex mirror, so it's a convex lens. Now, a diverging lens is the other type of lens, and that's sometimes referred to as a concave lens. For the same reason again, because it's like a cave that's forming on this side of the lens. Now this type of lens is thicker at the edges, not thicker, but thicker at the edges, right here, than in the middle, and it spreads light rays apart. The diagram isn't completely accurate here. The diagram should show the light rays are actually being spread apart after they encounter the lens. And so if you think about practically speaking, you may have heard someone being farsighted or nearsighted. Well, if someone is farsighted, they would need a converging lens, because what they can do is see things really far away very well, but things that are very close to them, their retina doesn't bend the light enough. And so they would need a converging lens. If someone is nearsighted, meaning they can't see things right in front of them very well, it's because the retina doesn't bend the light away well enough. And so they would need a diverging lens. Now this is something that some of you may look into in a project later on this week. But for now, it's just worth noting that the first type of converging lens causes the light rays to come together quicker, and a diverging causes them to move away and apart more quickly. All right, so with those two things in mind, let's move on to the next thing. Ray diagrams. Now we're not going to do a lot of work on ray diagrams for today. However, I'm going to introduce you just to how these are drawn so you can at least see them. The key thing I want you to get here is where the image is formed and what the location, orientation, size, and type are. So let's go ahead and do this. So as you would probably expect, we have a light ray that's going to come in towards the lens parallel to the principal axis, just like we had in a mirror ray diagram. And then that light is going to bend through the focal point. Now there's a focal point on both sides of this lens and of every lens, but in this case, because it's being converging, it's going to bend towards the focal point after the lens. And so let's draw that ray. So it bends going through the focal point and continues on. Now you'll notice that I'm only redirecting the light ray smack in the middle of the lens, and that's because it's bending slightly in the lens and then it bends as it comes back out of the lens. And so this is the way we're able to accurately draw it without having to represent what's actually happening inside of the lens. So let's do another ray. The second ray is going to come from the top of the object, and it's going to come through the focal point now on the left side of the lens. Again, that's going to converge, meaning it's going to bend it towards the focal point. It's not going to be able to bend it all the way up to the focal point, but it is going to bend it so it comes off parallel to the principal axis. And so what we get is these two rays coming together right here on the other side of the mirror. Now, if we were to draw the image, we would draw it right like that. Now you'll notice I've only drawn two rays, and the third ray has always just been a check to make sure we're on the right track. So the third ray, in the case of a ray diagram, is going to go smack through the middle of the lens right on the principal axis. So I'm going to draw that one as well just to check it. So there you go. That ray goes straight through the middle of the lens, right where it meets the principal axis, right there, and it continues on all the way down, and it meets in the same place as the other two rays. We then, I've already done it, but we could, at that point, draw that image, which we can see is larger, slightly larger than the other one. So let's go ahead and identify the location, orientation, size, and type. The location is further or farther from the lens than the object. It's a little bit further. We also recognize that it is inverted. It's upside down. The size is larger, and the type, We call this real because these are the actual rays of light that are coming together to form this image. So the thing that you're really wanting to identify right now is just the location, orientation, size, and type. And then we're going to have another day to practice these ray diagrams in our next lesson. Now what happens if we put the object inside the focal point? So here we're well inside the focal point. So this would be something very, very close to your eye, for example. And the first thing I'm going to do, just as before, I'm going to draw a ray that's coming parallel to the principal axis, and it's going to bend through the F on the other side. Then I'm going to draw another ray that lines up with F on the left side and then bends off parallel to the principal axis on the right side. So let's go ahead and do that. So there's my first ray in green, coming parallel to the principal axis, bending through the focal point on the other side. Then my second ray is lined up with this focal point there, and it bends off, coming out parallel to the principal axis on the right side. We have a problem. This converging lens is not actually bringing these light rays together on the right side. It's still bringing them closer, it seems, together than they are on the left, but it's not bringing them quite together. So how do we deal with that? Well, the way we deal with that is we trace the refracted ray back on the left side of the lens. So what I had to do is I had to take those refracted rays and then trace them as dotted lines back behind the lens. And what that gives me where those join is it gives me a point right there, which means that the image, always sitting on the principal axis, is going to be larger and upright in this case. So let's just draw that last line through the center of the lens to make sure that we have it right. Now you can see as I have to go back and actually make some small adjustments, this blue line was a little bit high. It went a little bit higher than the principal axis. It wasn't quite parallel to it. So I've made that adjustment. Try to make these lines behind more straight, which you should be able to do really well with a ruler. I can't necessarily do this dotted line with a ruler on the computer here. But you can see there that they all come together at the same point, and that would be where the image is formed. And so the location is farther from the lens than the object. Farther from the lens than the object. It's also worth noting that it's on the same side, not the opposite side in this case. Its orientation is upright. Its size is larger. And its type, in this case, because we're using the dotted lines to join it together, is virtual. They're not the actual light rays that are forming this image. And so those are the two cases that we have for a converging lens, otherwise known as a convex lens. Now a diverging lens is only going to have one case. It's always going to form an image with the same four characteristics. And let's see why that's the case. Here's why. Here's the light ray coming off of the object, and it's coming into the diverging lens. Instead of bending towards the focal point like it did with the converging lens, it's going to bend away from it and line up with the focal point over on the other side. So here I've drawn the first two rays. I'm just going to walk through what they are and how they work here. The first ray is this blue one coming off the top, and it's going to then bend, lined up, as I said, with the focal point over here. So it's coming in parallel to the principal axis, lines up with the focal point on the left side. The next ray, because it's diverging, is going to come in towards the focal point on the other side and then come off parallel. So you clearly see that these have diverged apart. They've come in from something inside the focal point, and those lenses have come apart. Those light rays have come apart even more. So where do we actually join them together? Well, we join them together on the left side of the lens. So you can see I've taken the refracted ray and I've drawn them as dotted lines on the left side of the lens. Now you can do a better job of this with a ruler. I can't draw a dotted line with the ruler function here, but you could draw that really accurately and find out where that is. Now we're just going to draw the last line, which is exactly the same for concave or for converging and diverging lenses. It's going to go straight through the middle of the lens and keep going straight. So let's do that. So there's that third ray, and you can see that it passes through the same point as the other two refracted rays were when they were traced back to the same side as of the lenses they came from. And so this is going to form an image that's smaller than the object, as we can clearly see. So the location here is closer to the lens than the object. Not only that, we could say it's inside F. The orientation is upright. The size is smaller. and the type is virtual because we've used these dotted rays to make it happen. And so why is this always the case? Well, you might ask yourself, well, can't we put an object outside of F? Well, let's do that and see. It might be hard to see on top of it, but I've drawn the rays in black, but I've drawn another object here that's outside of the focal point here. The focal point's the dot. And so in this case, we've got the one ray coming in parallel, going off, lined up with the focal point over here. We've got another one that comes in lined up with the focal point over here and comes off parallel. You'll notice again those diverge. And so if we trace these rays behind the mirror as dotted lines, we're going to get something that looks like this. Again, it's going to be smaller, upright, virtual, and closer to the lens than the object, just as we found in the other case. So that's why there's only one case for a diverging lens. The last thing I want to mention in this lesson is chromatic aberration. Chromatic aberration is the dispersion of light into different colors through a lens, as shown below. This occurs when rays of light bend far away from the principal axis. So forgive me for this terrible drawing here, but we all know that when we shine white light into a prism in the corner, that bends as it enters the glass, and then it bends again as it exits the glass. And what happens is that white light is dispersed into all the colors of the rainbow. Well, that's what's happening at the edge of many lenses. This chromatic aberration happens at the edge, not so much the middle because the light isn't bent as much, but towards the edge. And so as that's dispersed into the different colors, what you'll often see in a picture is the further out you go on the edges, you start seeing this rainbow effect. And it's because you have the exact same thing happening as happens in a prism.